Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capella High School. I want to welcome you to this lesson on significance tests. You will need your calculator at the end of this lesson. Before 1900, statistics meant observing data and calculating summary statistics such as means and standard deviations and variances. There was no such thing as inferential statistics. During the decade from 1915 to 1925, R.A. Fisher pioneered the fundamental concepts of inferential statistics, and that's what we're going to learn in this unit. A hypothesis test is a method that uses sample data to decide between two competing claims or hypotheses about the population characteristic. Let's consider a criminal trial. First thing that we're going to do is we're going to set the hypotheses. What is the null hypothesis? That the defendant is not guilty. This is what we assume at the beginning of the trial. What is the alternative hypothesis? That the defendant is guilty. The jury tries to determine whether the evidence supports the alternative hypothesis, and the standard is the beyond the reasonable doubt standard. That's the basis for making a decision. The null hypothesis is denoted H subscript 0 and read H naught. The null hypothesis is a claim about a population characteristic that is initially assumed to be true. It is the claim we seek evidence against. So we're going to create sampling distributions for the statistic based on our null hypothesis. And I have a note here, hypothesis statements are always about the population, never about the sample. So in your hypothesis statement, you should not refer to the sample statistic, the sample mean, the sample standard deviation, sample proportion, anything like that. So here's the format for the null hypothesis. The null hypothesis is that the parameter is equal to some hypothesized value. And I give as an example, the mean height is 64 inches. The null hypothesis is a statement of no relationship, no effect, no change, no difference, or contains the equal sign. The alternative hypothesis, also called the research hypothesis, is the competing claim for which evidence is being collected. The alternative hypothesis is denoted H with the subscript A or H with the subscript 1. To determine what the alternative hypothesis should be, you need to keep the research objectives in mind. And let's give an example. The alternative hypothesis here is that the parameter is not equal to the hypothesized value. And I give as this example, the mean height is not 64 inches. This type of alternative hypothesis, the type with a not equal sign, is called a two-sided or two-tailed test because we are interested in deviations on either side of the null hypothesis. Now notice that the alternative hypothesis uses the same population characteristic, mu, and the same hypothesized value, 64 inches, as we used in the null hypothesis. And here's the other type of alternative hypothesis with a greater than or a less than sign. And I give as my example, the mean height is greater than 64 inches. The alternative hypothesis with the greater than or less than sign are called one-sided or one-tailed because they specify deviations in just one direction. How do you decide which test to use, the two-tailed or the one-tailed test? We're going to look for keywords. Choose the two-tailed form of the alternative hypothesis when the question has keywords like different or not equal to. Choose the one-tailed form of the alternative hypothesis when the question has keywords like less than, more than, smaller than, or greater than. In practice, in the real world of research, we should use the one-tailed test only when we have good reason to expect that the difference will be in just one direction. Now here I have a graphical display of these two different types of alternative hypothesis. On the top, I have one-tailed tests, which look for deviations in one direction, deviations from the null hypothesized value. And in the bottom, I have a two-tailed test, which looks for deviations from the hypothesized value in two directions. Let's practice writing hypothesis statements. A study finds that the national average height of 12th grade women is 64 inches, and we want to know, is this true for the 12th grade women here at Capella High School? The first thing that we always do is we're going to define our parameter, in this case, mean CHS, that's what I'm going to call it, the mean height, and it's going to be defined as the mean height of 12th grade women at Capella High School. Then I have to state my hypotheses. The null hypothesis is that the mean is equal to 64 inches. The alternative is that it is not equal to 64 inches. I choose the not equal sign, the two-tailed test, because we're asking, is this true of 12th grade women at CHS? Now, whenever you're asked to write a hypothesis statement, the first thing I want you to do is to define the parameter, just as I've done right here. Also, do not mention the sample or the data when you're writing your hypotheses. To make it clear that you are not dealing with a sample, I suggest that you use the future tense when when defining your parameter. On the Texas driver's test, about 40% pass the test on the first try. Do students at CHS have a higher passing rate? Well, the first thing we do is define our parameter. So my parameter is rho, and I'm going to define it as the true proportion of CHS students that pass the driver's test on their first try. My null hypothesis is that rho is equal to 0.4. The alternative is that it is greater than 0.4. I use the greater than sign because the question, I see the keyword up there, higher, looking for a higher passing rate at Capella High School. This slide illustrates hypothesis involving a proportion. In my definition of the parameter, I use the word true to make clear that we are talking about the population of all CHS students. And we have another one here. Do fourth graders at Denton Creek perform better in math than do fourth graders at Lakeside? This could be measured by comparing the mean math scores of these two groups. So this time I'm going to define both parameters, the mean score at Denton Creek and the mean score at Lakeside. Now, the question is, do fourth graders at Denton Creek perform better? So when I state my hypothesis, well, that's always going to have the equal sign. So here's my hypothesis that the mean at Denton Creek is equal to the mean at Lakeside, and equivalently, I could write it like this, that their difference is equal to 0. The alternative hypothesis, I use the greater than sign here because we're asking whether fourth graders at Denton Creek perform better. So we have a greater than sign, and I can write it in either of these two methods right here. This illustrates hypothesis statements for a one-tailed test for differences in means. Okay, same problem here basically, except this time we're asking, do fourth graders at Denton Creek perform differently in math? That's going to change my alternative hypothesis. So same definitions. This time my mean is the same as before, or excuse me, my null hypothesis is the same as before, but this time my alternative is that we use the not equal sign. Now, basically what I'm saying here is, with the null hypothesis, is that any apparent difference between these means is due to random chance. The alternative hypothesis is that there is, in fact, a true difference between these variables. Now it comes time to making a decision. Hypothesis tests are designed to measure the strength of evidence against the null hypothesis. It is the null hypothesis that is actually tested, not the alternative hypothesis. When performing a hypothesis test, you either reject the null or fail to reject the null. That's your only choices. And if the null hypothesis is rejected, this is taken as convincing or statistically significant evidence to support the alternative hypothesis. However, we don't say that the research hypothesis has been proven true, only that it has been supported. We never say a hypothesis has been proven true. Similarly, if we fail to reject the null hypothesis, we don't say that the null hypothesis is true or accepted or proven. The lack of statistical evidence to support the alternative hypothesis is not the same as evidence for the null hypothesis. The alternative hypothesis might have been true, but your statistical test wasn't strong enough to find it. So the conclusion, if you fail to reject the null, you never say that you accept the null. Only Chuck Norris can accept the null hypothesis. Suppose you want to know whether there was a skunk in the backyard the previous night. The null hypothesis is that there was no skunk in the yard. The alternative is that there was a skunk in the yard. If you find skunk fur and smell skunk, what conclusion would be appropriate? Well, I'm going to strike C and D immediately because we never accept a hypothesis. And E is wrong because we never say that a hypothesis is proven true. So now we're debating between A and B. What happened here is we found skunk fur and we smell skunk. That's evidence against the null hypothesis. So we're going to reject the null hypothesis. Change the facts a little bit. This time, if we don't find skunk fur or smell skunk, what conclusion would be appropriate? Well, we're going to eliminate C and D because we never accept hypotheses, and E is wrong because we never say one is proven true. Now we're again debating between A and B. We don't find skunk fur and smell skunk, so we don't have evidence against the null hypothesis, but we can't say that we accept the null. What we say here is we fail to reject the null hypothesis. And I know from an English perspective, failing to reject the null is clunky, and it might even be a double negative, maybe so. But from a statistical perspective, it is perfectly correct to say fail to reject the null hypothesis. Replacing that word with accepting the null would be wrong. We fail to reject the null hypothesis. So, after we set the hypothesis, the next thing we have to do is decide on the criteria for making a decision. Remember, in our criminal case, our criteria was the beyond a reasonable doubt standard. Now we have to choose a significance level. That will be our criteria for decision making. After we determine the null and alternative, the next step is to choose the probability levels for the test that would convince you that the result is more than just random error associated with the null hypothesis. In order to test hypotheses, we must decide on the level of probability to use as our cutoff for whether the null hypothesis will be rejected. This cutoff, this number, is sometimes called the critical value, or the significance level, or the alpha level. Now, common significance levels are the 10%, the 5%, or the 1%. You are familiar, no doubt you are familiar with cutoffs. How old do you have to be to vote? How old do you have to be to buy cigarettes? How old do you have to be to buy beer? How old do you have to be to serve in the military or be independent from your parents? These are cutoffs. And sometimes these cutoffs seem a bit arbitrary. Is a person who is 18.1 years old really that much more mature than one who is 17.9 years old? So that's what we're doing here. We're figuring out the cutoff that we're going to use for making our decision. The 5% significance level is the one that is most often chosen, but it is an arbitrary value. If the problem does not give you a significance level, this is the significance level that I want you to use. Now, science is infatuated with finding probabilities, p-values, that are less than 0.05. It means the difference between getting your results published or not. If you do not have a probability below 0.5, the results of your study will not be published, and that's kind of sad because many useful studies go unreported and unpublished because we are infatuated with the 5% significance level. The 95% confidence interval corresponds to a two-sided test at the 5% significance level, or alpha equals 5. So your 95% confidence interval will give you the same answer as your two-sided hypothesis test at the 5% significance level. A sample result is statistically significant at the 5% significance level if it would occur just by chance no more than 5% of the time in repeated samples when the null hypothesis is true. Now let's turn to p-values, and this is something that gives students trouble. The p-value is the probability, assuming that the null hypothesis is true, that the sample statistics, such as x bar or p hat, would be as extreme or more extreme than the actually observed outcome by random chance alone. That is the interpretation of the p-value. And so if you are asked to interpret the p-value, and this could occur on our tests, on AP exam, this is the format that I want you to use. This interpretation, this 26, is a conditional probability interpretation. So it begins like this. If the true, and you're going to insert proportion or mean, depending on what kind of study you're doing, were really, and here's where you insert the hypothesized value, then there is, and you're going to insert the p-value, probability of getting a test statistic as extreme or more extreme than ours by random chance alone. That is the interpretation. So I want to give you this. This isn't an example, but this is kind of an illustration of what the p-value tells you. Imagine that you have a coin that you suspect is weighted towards heads. Your null hypothesis is that the coin is fair. You flip it 100 times and get more heads than tails. The p-value won't tell you whether the coin is fair, but it will tell you the probability that you'd get at least as many heads as you did if the coin was in fact fair. P-values indicate how surprising the sample result would be if the null hypothesis was true. So let's give an example. In our test of whether CHS students have a passing rate greater than 40% on their first try of the state's driver's test, remember our null hypothesis was that rho is equal to 0.4, and the alternative is that rho is greater than 0.4. Suppose that CHS sample proportion of 47% had a p-value of 0.153. How would you interpret it? Okay, I'm going to just basically use the format that I had before, plugging in my numbers. If the true passing rate were really 0.4, then there is a 0.153 probability of getting a sample proportion equal to or greater than 0.47 by random chance alone. That is a model answer for interpreting a p-value for a proportion. P-values. A p-value describes the exact significance level associated with the result. If the p-value is small, say less than 5%, then it would be unlikely that our observed result could be attributed to random chance, assuming the null is true. So we would reject the null. Large p-values indicate that the observed value of the test statistic would not be unusual or not surprising if the null hypothesis were true. So we don't reject it. If the computed test statistic has a smaller p-value than the critical value, the alpha level, then the null hypothesis will be rejected. The reasoning is this: an outcome that is very unlikely if a claim is true is good evidence that the claim is not true. And here is the decision criteria. I've put it here in this slide, and this is I think my clearest description. A formal decision-making explicitly compares the p-value to the significance level. So when you're making your conclusion, you have to compare the p-value to the significance level. If the p-value is less than alpha, reject the null hypothesis. This is convincing evidence for the alternative hypothesis. If the p-value is greater than or equal to alpha, then we fail to reject the null hypothesis. This is not convincing evidence for the alternative hypothesis. Okay, let's give an example. This is how you're going to conclude your FRQs when you're doing testing a hypothesis. If the p-value is less than alpha, we reject the null hypothesis. Excuse me. If the p-value is less than alpha, we reject the null hypothesis and say that the result is statistically significant at the alpha level. In this case, we say because the p-value, and I insert the number, is less than alpha, then I insert that number, we reject the null. There is convincing or statistically significant evidence to believe the alternative hypothesis is true, that the alternative hypothesis that the true, and then you're going to describe the alternative hypothesis in context. If the p-value is greater than alpha, we fail to reject the null. In this case, we say because the p-value is greater than alpha, we fail to reject the null because we do not have convincing evidence to believe that the true, and here I insert the alternative hypothesis in context. Another example here, a p-value of 0.7 indicates that a sample statistic is statistically significant at the 93% confidence level. We would reject the null at the alpha equal 10 level, 0.10 level, but fail to reject the null at the alpha equals 0.05 level. If this is a two-tailed test, the sample statistic falls outside the 90% confidence interval, but inside the 95% confidence interval. Now, what affects the p-value? Increasing the number of observations generally drives down the p-value of a test when the truth of the population stays the same. Let's go over this quick example. For his second semester project in AP Stats, this student decided to investigate whether students at this school prefer name brand potato chips to generic potato chips. After collecting data, the student performed a significance test using the hypothesis that the null hypothesis is that rho is 0.5. The alternative is that rho is greater than 0.5. In this case, where rho is equal to the true proportion of students at his school who prefer the name brand chips. So you can see if rho is 0.5, then there's half of them prefer one and half prefer the other. The resulting p-value is 0.074. What conclusion would you make at each of the following significance levels? At the alpha equal 0.10, here's the conclusion. Because the p-value, and I insert its value, is less than alpha, and I insert its value, there is convincing evidence that students at the school prefer name brand chips. How about if the alpha is 0.05? In this case, because the p-value is greater than alpha, we fail to reject the null. There is not convincing evidence that the students at this school prefer name brand chips. And I leave you with this nice haiku. There you go.